All right, greetings everyone. The purpose of this video is to go over a pumping type problem, um, which is one of the types that you'll see in the physical application problems in our homework. All right, before we do an example, first want to draw your attention to a problem-solving strategy from our textbook that has a nice kind of set of steps you can follow to help you solve one of these problems. Now, these problems, depending on the setup you're given, they're all kind of different. So there's no like use this formula every time. So I can't give you that. But what I can do is give you this kind of framework for a problem solving strategy as something that you can, kind of a process you can follow each time that you do one of these problems. So first of all, as with a lot of real world problems, when you want to sketch a picture and select an appropriate frame of reference, and I'll explain more about what that means. Then we want to calculate the volume of a representative layer of water. So in these pumping problems, we'll be figuring out work, the amount of work needed to pump a certain amount of water out of some given container. And so what we're going to do is look at a kind of a layer of the water and calculate the volume. We're going to multiply that by weight density of water to get the force. Okay, so we need force in order to do work, because work is force over a distance. And then, the second part of that, the distance, we calculate the distance that the layer of water must be lifted. And then, as I mentioned, we multiply those two to get an estimate of the work needed to lift that single layer. And as you might imagine, if you have an amount of water, right, and you're going to lift a single layer, to pump it out, well, then you also have to pump other layers, right? And so we'd kind of look at the work done for each individual layer and then lift it out. However, since this is a calculus course, first of all, we want there to be an infinite number of layers. We want to add all that together. And so that's what 6 and 7 are talking about. And basically the moral of the story there is we end up doing an integral in order to find the amount of work. Okay. All right, so let's look at an example. So we're going to go through most of those steps that were on the previous slide. So we're given a trough that is full of water, that is 4 feet long and 1 foot high. It's an important piece of information there. And then the vertical cross sections parallel to the ends, vertical cross sections, look like the function y equals x to the fourth over x equals -1 to +1. And we need to find the amount of work in these odd units, which are foot-pounds, done to empty the trough by pumping water over the side. And so if we follow that process outlined on the previous slide, the first thing we need to do is sketch a picture and choose an appropriate frame of reference. Now that frame of reference part is usually referring to put this picture on a coordinate axis of some sort. Okay, because since we're going to be integrating, we want to be able to create some functions. We want to integrate some functions. And so in order to do that, we need our picture to sit on a set of vertical axes, or coordinate axes, excuse me. Now, the most obvious connection we have in this problem to coordinate axes would be this part about cross sections looking like y equals x to the fourth from x equals -1 to x equals 1. So what I'm going to do is draw a set of axes here. Okay. And I'm going to draw that function y equals x to the fourth from x equals -1 to x equals 1. So to do that, I'm going to mark -1, +1 on my horizontal axis here. I know that if I plug both of those into the function, so like if I do y equals 1 to the fourth, or I do y equals -1 to the fourth, either way I get +1. So I'm also going to mark +1 on the vertical axis. Okay, and then I'm going to draw the function y equals x to the fourth between those 2 points. So I'm not going to use that color though, use this color. So we know that at -1, the output will be 1. At +1, the output will also be 1. We also, you could probably see if we plug in 0, we get 0. And then we can kind of connect the dots there. We know that the shape of this should look something like this. Although we're just interested in that part from x equals 1 to x equals -1. So we're really only looking at this piece here. Okay. Now that gets us started with our picture. Now, those are vertical cross sections of the trough are supposed to look like that. And what that kind of means, if you think about it, is that those are kind of like the ends of the trough. So what I'm going to do actually is connect this across, whoops, but not like that. There we go. And then the trough is going to be 3-dimensional. So I'm going to kind of extend out the ends here. Okay, and because the vertical cross sections look like this kind of U shape, I know at the other end it'll be a similar shape. Okay, kind of like that. We could connect it across the bottom if we wanted to. Okay, so there is our picture. And again, this is nice to have it this way because it's got it imposed on a set of axes, which means we can work with some functions here. Okay, so let's look now with step 2, which is to sketch a representative layer of water and find the volume. And actually, this might be, yeah, this is step 2. I thought maybe it was steps 2 and 3 together, but it's just step 2. Okay, so for the representative layer of water, I'm going to kind of draw it in here. So it's going to be like kind of a single layer here. And something like this. And I know it's probably hard to tell my picture here, so I'll sketch it over here. Basically what I'm doing is creating a layer that looks like this. Okay. And we want to figure out what the volume of that representative layer is. And again, if you're wondering why I'm doing that or why I thought of it that way, hopefully you can see that I could draw, another layer, whoops, kind of below it, and another layer below that, and kind of mark off all the different layers of the trough from top to bottom. Okay. Now I'm not necessarily giving them an exact width, and we'll talk about that, or excuse me, height. We'll talk about that as we work on this. This just kind of gives me something to reference. Okay, and then I also want to look at finding the volume of that, and that's really what step 2 is, finding that volume of that representative layer of water. Now notice that the shape that we've got here is more or less a rectangular box, and I can mark the length, I'll call this the width. Actually, that doesn't make any sense. Let me do it the other way. We'll make this the width, this the length, and then the height here. And for volume of something like this, we do length times width times height. Okay. And now we need to fill these in. Well, the length, luckily we can do fairly straightforward because that's going to be the length. Well, it'll be the length this way, which on the trough would be along this way, which notice that that's just whatever the length of the trough is. And we're told in the problem that that is 4 feet long. So we know that what goes here is 4 for the length. The width is a little bit more tricky. So the width in our picture is this part here, which goes across here. And this is one where we're going to have to write it in terms of variables. Now notice that if we look at, say, the distance from the horizontal axis over, right, for that layer, it lines up with some point on the function y equals x to the fourth, which corresponds to some x value down here, right? Now, we don't know exactly where that x value is, whether it's like 0.8 or 0.7 or 0.4. But notice that the value we have to go over to that x, or the length we have to go over to that x, is the same as this distance, this kind of half distance of the width of the water, right? This and this are the same. And notice that it would be a similar idea going in the opposite direction, right? It would be over to here, which because of symmetry would be at the negative x value. But however, that physical distance there would be the same as this one here. And again, we're saying that this distance is x units long. So this one would also be x units long, which means that our full width there would be x plus x, or 2x. Oops, not 2w, 2x. Okay, so our width is 2 times whatever the x value is for this particular layer. And then our height, we're going to fudge here a little bit. I guess it's not really fudge, but be a little less specific. Because I don't really choose a specific height for the box. And in fact, as you might imagine based on what I explained, we're going to want to do an infinite number of layers here. And so as we do that, that height is actually going to get smaller and smaller. But notice that it relates to a distance on the vertical axis, right? So that height here, so this height here, we relate to a height here to relate to a height on the vertical axis, right? And again, we don't know exactly what it is, but it's a change on that vertical axis that we're not aware of, but we know that often the variable on the vertical axis is y. So I know I'm going to call it dy because it's some change in a y value right there, okay? So it's some distance on the y value, so we're on the y-axis or the vertical axis, so I'm going to call that dy. So our height here will be dy. If we multiply this out, we have 4 times 2x times dy, which give us that our volume is 8x dy. Okay. All right. So we've got our volume. So we can move on to step 3 of our process here. I'll have to go on to another slide here. So step 3 is where we multiply by the the weight density of water. So right now we've got that our volume of our representative layer here is 8x dy. And we're going to multiply that by the weight density of water. Now, the weight density of water, I'm sure you know off the top of your head, is 62 pounds per feet cubed. And that was a joke. I don't actually expect you to know that number off the top of your head. So I'm going to take our volume here and multiply it by that. And so what we end up with is if we do 8x dy by 62, all we can multiply here are the two numbers because the other things are variables. And so when we do that, we end up with 496 x times dy. Okay. All right. In case you're wondering what's going on there, first I want to go back here. Notice first of all that all the information we were given in the problem is in terms of feet, right? So it's 4 feet long, it's 1 foot high. And we can expect that all the distances here are in feet. So when we find a volume in feet, right? So volume is units cubed, so that's going to be feet cubed. When we multiply by that weight density of water, well, I told you the units of that were pounds per feet cubed. And notice that when we multiply these, we can multiply the units. So I'd have like feet cubed over 1 times pounds over feet cubed. The feet cubed can cancel, and we're just left with pounds. And if you've taken physics, you may know that pounds is a force measurement. Okay, so that's good because now we have something that gives us our force on that representative layer of water. Okay, which we need force in order to calculate work. All right, so then let's look at the fourth step. Okay, so the fourth step of our process is to calculate the distance that representative layer of water needs to be lifted in order to be pumped out of the trough. Now I'm going to try to do a real quick sketch here of our trough again and our representative layer of water. Okay, so there's our trough. Here's our layer of water. Okay. And notice that right now, the layer of water right now, I shouldn't say right now, I should say where it is, the layer of water is sitting at some value y, right? Some height y, in fact. We could say that the distance up to that layer of water is y. Now, I know it's not exactly that because, there's that dy, that actual height of the water, but for now, let's just say it's y. And to be lifted out of the trough, it has to be lifted this remaining distance to the top of the trough, right? So the question is, what is that distance? Well, recall, first of all, that the point where our function here crosses the vertical axis, that's at y equals 1. And so that distance, well, first of all, I know that this distance from 0, 0 up to the layer of water, that's some value y, it's some height y. And so the remaining distance up here that the water has to be the representative layer of water needs to be lifted would be 1, since that's the top value, minus this y value, because that would tell us what is left over here in the middle. Okay. So our representative distance, or sorry, our distance here that this is being lifted would be 1 minus y. Okay, again, because it's that leftover remaining part at the top there that the water has to be lifted out. All right, good. So we have our distance now. So we can do our fifth step. Fifth step, which is we multiply force times distance. So we're going to take our force to lift the water times the distance the water is being lifted. And our force, remember we found back here, that's the 496x dy. Our distance is this 1 minus y. So we end up with doing 496x dy times 1 minus y. And since a lot of variables and some parentheses there, we're not going to simplify this much right now. We'll just maybe move things around. So we're going to write this as 496x times 1 minus y dy. Okay. And so that represents the amount of work that needs to be done for that layer. Okay, so again, we could go through and do this for all different layers of water in the trough, right? I could, as I showed before, just keep drawing more layers here and do this similar calculation. And then to get the total work, we would need to add those together, right? So we'd sum a bunch of expressions like this. But we want to get and in the way I've drawn it, that sum would give us an approximation, right? Because we have all of these boxes that are, boxy shape, not the smooth curve like it is inside the trough. So there'd be some stuff missing and whatnot. So that wouldn't give us the exact value. So what we would do is actually use more layers in order to get an exact value. And in fact, the number of layers we prefer to use is an infinite number. But when we sum an infinite number of things, as you may have figured out in this class, what we end up getting is an integral. And so this is kind of steps 6 and 7 together, is that we need to integrate that function that we came up with, or the value or the expression we came up with for the amount of work, which would be 496x times 1 minus y dy, right? And yeah, so this is kind of representing all the different layers for all the different X and Y values. Okay, so now in order to integrate this, there's a couple of things we need to resolve. First of all, notice that we have both X's and Y's in the integral, so we need to fix that. We also need some bounds of integration, right? Now, in order to do that, we should first figure out whether we're going to integrate with respect to X or to Y. Now, note, we have a dy here, so that tells us we probably want to integrate with respect to Y, which means we need to rewrite this X in terms of Y's. Luckily, we have a relationship between X and Y that we can use, so we know that we have that equation y equals x to the fourth. So we can solve for X there by taking the fourth root on both sides. And so when we do that, that gives us X equals fourth root of Y. But another way to write that is Y to the 1/4. And so we'll go ahead and drop that in for X here. So our integral now becomes 496x, or sorry, not x. That was the whole point, Cody, was to get rid of that. 496 times y to the 1/4 times 1 minus y dy. We were about there. Now we just need to get some bounds of integration. And if we again go back to our picture here, remember that our trough looks something like this. Okay, and remember we're integrating with respect to y, so we want to think about what are the y values we're covering. Well, we're basically going, all our layers are going from down here, right? That's the lowest possible it could be, to up here, which is the highest possible it could be, right? And since our function here is y equals x to the fourth, going from, sorry, I keep hitting the wrong buttons, going from x equals -1 to x equals +1, and that gives us output of 1 there. And then we know this down here is at 0. It looks like the values we're covering on the vertical axis, the y values, go from 0 to 1, right? So our bounds of integration would be 0. Gosh, sorry. Here we go. From 0 to 1. Okay. And we can integrate that. I'm not going to go through all the steps of that right now. Leave that to you. I would say you'd want to distribute this into here before you integrated. And when you do that, you can check my work on this. I do believe we get 176.356 as our amount of work. And our units there, if you remember back, the 496x dy, that was the force in pounds. The 1 minus y, that's the distance in feet. We multiplied those two. So our units end up being this pounds times foot units, which may seem strange, but you can talk to your physics professors. It's a real thing. I didn't make it up. Okay. All right, one more thing before we end this video is I just want to talk about doing these units or doing these problems in metric units. So there's a little bit of an extra step here. So, as we saw in the previous one, we have to find volume of something. Typically in metric units, that's going to be meters cubed. You'll be doing things in meters. And then we have to do that volume times density calculation, right? Well, our density in metric units is 1,000 kilograms per meter cubed. And so when we do a volume times that, we kind of do in a similar calculation that we did before, meters cubed times kilograms per meters cubed. These cancel out, and we're just left with kilograms. Okay. But in using the imperial units, the American units, when we did this calculation, this volume times density calculation, we got pounds, which is a force. However, in metric, kilograms is a mass. It's not a force. So we need to use it to turn it into a force. So in order to do that, once we have this mass value, we need to do an extra step, where we take it and multiply it by acceleration, because you may remember from one of Newton's laws that force is given by mass times acceleration. And so we take that and multiply whatever we get for our mass, by acceleration, which acceleration due to gravity on Earth is 9.8 meters per second squared. So you need to do the extra step of multiplying by this after you've done your volume times your density. Okay. All right. Well, that's it for now. Thank you so much for watching.